Here we're going to introduce quadratic functions and the two basic approaches to solve quadratic function. Y equals ax squared plus bx plus c. So this is an expression with three terms: ax squared, known as the quadratic term, bx is a linear term, and c is a constant term. The only requirement for this quadratic function to be quadratic is the coefficient for the quadratic term a is non-zero. And this is, of course, kind of obvious, right? If the quadratic term a, constant coefficient a is 0, then the quadratic term is gone. So an important question for this quadratic function is to find its zeros. What do we mean by its zeros? Zeros are the x such that ax squared plus bx plus c equals 0. So the x such that this equation holds are called the zeros for this quadratic function. Or rather, we all know that this is just the roots for this quadratic function. So how we solve this? Before we start, we can look at something we have learned before. It's a linear equation. A general linear equation is ax plus b. And when we try to solve this, we say ax equals b equals plus b equals 0. And how we solve it? This is just very simple algebra. This is equivalent to ax equal negative b, and then the solution x is going to equal minus b over a. And clearly that we require a not equal to 0. Otherwise, this is not even a linear equation. So how we solve a quadratic equation like ax squared plus bx plus c equals 0? This is not as simple as a linear equation, but turns out there are exact formulas for the solutions to this quadratic function. And here we're going to introduce two basic approaches to this. And we're going to see it from intuitive reasoning. And I'm going to help you to go through the thinking, and hopefully we can derive it by ourselves. So there are two basic approaches to this, and both are learning from simple cases. So what do we mean by simple cases? For this quadratic equation, ax squared plus bx plus c equals 0, there are three terms, right? The quadratic term, the linear term, and the constant term. We're going to consider two special cases. One is when b equals 0. If b equals 0. Now, terms, examples like this, for example, example 1. Let's say x squared minus 16 equals 0. So in here, the constant coefficient for the quadratic term is 1, a equals 1, and c equals negative 16. But b is equal 0 for the general form, right? A equals 1, c equals minus 16, b equals 0, you get x squared minus 16 equals 0. Do we know how to solve this kind of quadratic equation? Of course we can, right? This is very simple. We just let x squared move the constant minus 16 to the other side. By plus 16 to both sides of the equation, we have x squared equals 16. Now for x squared equals 16, this, we're going to take the square root of 16, but don't forget there is a negative root, right? So x is going to equal either the plus square root of 16 equals 4, or x equals negative square root 16 equals -4. So you see, when b equals 0, we basically know how to solve this because this is just taking the square root of the constant. Let's look at another example, just slightly more complicated, only because the numbers are less friendly than 16. So let's look at 4x squared minus, let's say, equal 10, minus 10 equals 0. So in this case, of course, we do the same thing. So this means that 4x squared is going to equal 10. So that means x squared is going to equal, when I divide by 4 to both sides of the equation, we have x squared equal 10 over 4 equals 5 over 2. Now, again, we're going to take the square root of both sides of the equation. X squared equals 5 over 2. We get x equals plus square root of 5 over 2, which we're going to simplify this radical, which equals 2 of square root 10. 10 divided by square root 2, right? Inside this, the square root, we're going to multiply 2 to numerator and denominator at the same time, which we now can pull out this perfect square in the denominator, out of 2. So square root 10 divided by 2. Or we have the negative root 5 over 2 equals negative square root 10 over 2. So you see that if b equals 0, we can solve this quadratic equation by the following. Plus c equals 0, because the b is 0, so we can get rid of the linear term. We have this, so which means that ax squared equals negative c, which means that x squared equals negative c over a. At this point, you should realize that in here, c over a has to be less than 0 for this equation to make sense if x is real. And of course, we have not gone to the imaginary complex numbers, so we're living in this real world here. So x is real, then c over a has to be less than 0 because x squared has to be non-negative. C over a has to be less than or equal to 0. If this is true, then x is going to equal either the plus square root of negative c over a, or x equals negative c over a. Now, obviously, when we have actual numbers for c over a, we need to simplify this radical, right? But that's kind of the detail of the exact solution. The real solution is just square root of minus c over a and take the plus negative sign. So if b equals 0, we know how to solve this. It turns out very simple. Now, of course, the question here is, what if b is not 0? And this leads to the solution by the name called completed square. When we have b terms, we're going to somehow pull out b into the x squared. Combine that together becomes a x squared term, and we can solve that. And this is complete the square technique, which leads to the quadratic formula. This is one way to derive the quadratic formula. And we're going to do that in the next, some class down the road. In this lecture, we're going to mainly focus on the second approach, another simple case. So let's look at this. So we already considered a special case 1 or simple case 1. When b equals 0, right? And here we're going to look at special case 2. When c equals 0. So that in the general form, ax squared plus bx plus c equals 0. Now we have the c is equal 0. So let's look at an example 1. X squared plus x equals 0. How we solve this quadratic equation. Now in this, you realize the constant term c is 0. The linear term b, coefficient b, is 1. And the quadratic term with constant coefficient a also equals 1. How we solve this? The idea of this is using the factoring technique. We know that x squared plus x is equal to x times x plus 1. This is, of course, just opposite direction of the distributive law. There's a common term in every term, so x squared plus x, there's an x common to x squared and x. So we pull the x out and left with x plus 1, x times x plus 1. Now for this equals 0, here we are going to remember a very simple property. If I have a bunch of terms, a bunch of expressions, let's say expression 1 times expression 2 times expression 3 and time maybe expression many terms, okay, expression 10 equals 0. Then if you have these expressions multiplied together equals 0, you know one of the term has to equal 0. Right, this is a very, very simple yet powerful property. If I have a bunch of terms multiplied together equals 0, then one of the term has to be 0. And this is the basic property to solve this when I can factor the quadratic term. So when I have x times x plus 1 equals 0, we know that either x equals 0 or x plus 1 has to equal 0. You only have two possibilities. For all the other if this is not 0 and this is not 0, then multiply together cannot be 0, right? That's the basic property, where the basic property comes from. So you have x0 or x plus 1 equals 0. And that gave you the two solutions of x such that x squared plus x equals 0. Either x equals 0 or x equals -1. Because you can solve this because this is just a linear equation. All right, let's look at another example, just slightly more complicated, I guess. Example 2. You have 4x squared minus 6x equals 0. Now in here, again, we'll remind ourselves that in here, the constant coefficient for the quadratic term a is 4, and b is -6, and c, of course, is 0. Again, for this, we're going to factor this, the left side, which you have the constant, you have a common x to both terms. In fact, you have 2x to both terms. So I'm going to factor this out, 2x, and inside is 2x minus 3 equals 0. Now again, when we have the two terms multiplied together equals 0, we know that either this equals 0 or this equals 0. So let's just list it out. Actually, by the way, the 2 times x times 2x minus 3, the 2 we can just ignore because 2 is non-zero. So for these three terms multiplied together equals 0, either x equals 0 or 2x minus 3 equals 0. So we have the two solutions, x equals 0 or x equals 3/2 by solving 2x minus 3 equals 0. I'm moving the 3 to the other side and divide by 2 to both sides of the equation. So that's the solution to this quadratic equation. In general, if the c equals 0, then we are solving this special case of quadratic function ax squared plus bx equals 0. We know how to solve it by pull the x out and inside is x plus b equals 0. And we get two solutions, x either equals 0 or ax plus b equals 0. So x equals minus b over a. X equals 0 or x equals minus b over a. And we know these are the only two solutions to this quadratic equation, because if x is not 0 and this is not 0, then they multiply together cannot be 0. So we know that this are the only two solutions to the quadratic function. So now we know there's a special case when c equals 0, this we can solve. But then try to focus back a little bit. What's the idea that we can solve this ax squared plus bx equals 0? The reason we solve it, because we factor this left side into the product of two terms. So can we generalize this approach to solve a general ax squared plus bx plus c equals 0? By that, I mean is, can we factor the left side into something like, ax plus p times x plus q. And if we can, then equals 0, then we can solve this quadratic equation by knowing that one of the terms has to equal 0, and we solve it. And this is the basic idea of solving quadratics by factoring. And we're going to talk about in the next lecture.